Global Supplier Quality Assurance Organization at Spirit Aerosystems. I am also a member of the IAQG 9145 deployment team. Mark and Peter, can you go ahead and introduce yourselves real quick?
Sure, this is Peter Papadopoulos with Pratt Whitney as a senior fellow discipline lead, and I'll be talking about process capability and control a little bit later.
Mark Little from Collins Aerospace, also part of the APQP deployment team, and I'll be talking about key characteristics.
Thank you, gentlemen. Unfortunately, I can't seem to switch the slide. One more, please. Thank you. Real quickly, let's just go through the agenda of today's webinar. Sue has already gone through the webinar tips. We're going to start diving right into the process capability and control variation management portion. Then we'll go into questions and answers, and then we'll also go through some SCMH information on how to access the SCMH. So welcome to Process Capability and Control portion of the APQP and PPAP webinar series. Our objectives today within this webinar is to provide you with a high-level understanding of process capability and control, introduce you to the APQP tools, SPC and CpK, and show how they relate to 9145, share best practices as well as benefits, and to provide you with additional sources of information. By the end of this webinar, participants will be able to understand the key components of variation management, understand how to measure CPK and SPC, and understand why KCs are important to apply to variation management. As we move through the webinar series, we are now in the process capability and control step in our APQP roadmap. The webinar following will be focused on PPAP. Let's go ahead and get into variation management. What is variation? Variation is a change or slight difference in a condition, level, or amount typically within certain limits. No two products or processes are exactly alike because they contain many sources of variation. The variation may be large or very small, however, they are always present. The problems do occur, however, when the total variation exceeds the customer expectations. For example, parts that are within specification tolerances are acceptable, but parts out of specification tolerance are not acceptable. There are two types of process variation. The first is common causes. This type of variation is predictable and part of the normal process. They are difficult to eliminate, however, with proper control should be manageable. Some common examples include poor maintenance of machines, normal wear and tear, insufficient training, not one way of working, poor working conditions, measurement errors, and ambient temperature or humidity. The second type of process variation is also known as special causes or assignable causes. This type of variation is easily detected and corrected. Examples of this types of variation include poor batch material, inexperienced operator, out-of-date drawings, tool damage, maintenance check overlooked, misread drawings, or planning instructions and machine breakdown. Did someone push the slide? I'm sorry, for some reason I can't move the slide again. Thank you. Why do we manage variation? Variation of some sort is responsible for all nonconformances and or customer satisfaction. Nonconformances cause delays and cost money. By reducing the amount of variation, we reduce the risk of nonconformances and improve ease of assembly. By putting process controls in place, it helps to identify and manage the different types of variation, the amount of variation, and how well the processes will meet customer requirements. Once we understand how variation exists and the sources of variation, we can take the proper steps to reduce it. Now I'm going to pass the presentation over to Peter, who's going to discuss with us capability analysis in SPC.
All right. Hopefully everyone can hear me okay. I know at least one person said I sound a little bit fuzzy. I may be having some computer issues today. But today what we're going to talk about, as I mentioned, is capability and process control, or also called SPC. In general, when we run a process capability, we should always run a process control check to make sure that we understand that the variation we're seeing is predictable over time. Otherwise, we won't be able to trust our process capability. Now, what is process capability? In general, it's a set of tools that we use to understand whether or not our process is capable. And what does capability mean? Well, one of the things I like to say is capability is how good your process can be and is operating at. One thing I will also say is that I've heard people say, is your process capable, yes or no? The answer is it's not binary. It's either it's capable to within a certain limit, or it's capable to within a certain percentage of defects or some such, or you can use the capability indices. Either way, that's what we're going to be talking about today, is how to express your process in terms of a capability. And really, again, it's to express the quality level of your process, and if someone ever asks you, is your process capable, you should be looking at them funny and saying, I'm not sure if I can answer that question, because there's not yes or no answer. It should be, what is the quality level of that process? All right, so when we talk about process capability, what we're really talking about is understanding what the process is doing when we compare it to the voice of the process versus the voice of the customer. The actual voice of the process is when we talk about the process and what it's actually doing, the measurements we're getting, the variation that we're seeing, and we compare that against what our customer wants to see. In other words, a feature or a pass-fail goodness, or is it functioning well? We compare what we're getting out of our process against that, and then we can actually report what we call a process capability. All right. Now, sometimes we have internal process specifications, which are fine, or feature specifications. They may be tighter because we want to make sure we control it more than our customer wants, and we can actually create a capability against that number. And one thing I always want to caution against as well is that spec limits are independent of control limits, right? They're two different things. Again, the control limits are the voice of the process, and the spec limits are the voice of the customer, right? And when we compare, again, as depicted in the picture, the width of the distribution of the process against those spec limits, that is actually what we call process capability. All right, now, to understand process capability, before we even get into giving an indices or an answer of what is that process capable or not, or what is it capable to, you have to understand the process has to be characterized. In other words, what type of data are you going to be gathering to characterize this process? Is it attribute or variable? Is it representative of the actual process that you're running? Is the variation over time understood? And how many samples do I need to take to understand that variation over time? And that's going to give me information on the short and long-term variation that I'm going to see of that data, and that's the data I'm going to collect. And one last little bit of process characterization is rational subgroups. What are rational subgroups and how do they use them? Right. Overall, the process is characterized by the data it generates, and we're going to be going through each one of these areas on the next few slides. All right, data types. The first thing you should be realizing is that the data that you're going to be gathering is really truly going to affect your process capability study, your control charts, and your indices, how you're going to be calculating your CpKs or your process capabilities. That being said, let's describe them. Attribute data is any data that typically is defined either binary or on some type of discrete scale. But it's going to be a name of sorts, pass versus fail, good versus bad. And typically, the way we describe capability on those is just the percent good and the percent bad. But we do have to have some type of spec or some type of criteria that tells us what is good or bad. So getting back to what I mentioned before, I'm comparing my process versus the voice of the customer, what is good and bad. On the other side, we have continuous data. And in continuous data, it's defined as a spec limit, right, compared to my process. And again, same idea though, I'm going to compare how many good parts I'm getting versus defective parts, and that's really my process capability. Again, they look very different when it comes to, you know, what you're going to be reporting out on and graphically, but it's still the same process capability, and we can still use the same indices. All right, so what are these indices that are typically used to describe process capability? Well, if you have attribute data, you're going to be describing it either as a ppm, you know, parts per million defective, or percent defective. Now, that can be turned in what they call a defects per million opportunities or defects per million parts. And once you have that, you can turn it to a Z-table, which is called a Z-score or a sigma level. If you have variable data, CPs, PPs, CPKs, and PPKs are indices that are typically used for that because you can use the mean and standard deviation to calculate that. Those can be turned again into DPMOs or DPMs, which is basically how many defects you're getting out of a million. And that can be turned again to a sigma score, sigma level, Z-score, or whatever you want to call it, and is a common, doesn't matter if it's variable attribute. So again, these are the typical indices that you see. Attribute versus variable can be different ones to start with, but they can all be converted to a common one, whether it's DPM, DPPM, DPMO, or sigma level or Z-score. So those are the typical indices that we're going to be using. Now, let's describe a little bit what those two, especially variable indices are, the CP, CPK, and PP and PPK. Now, if you're looking at CP and PP, those assume that the process is centered and just really relates the standard deviation to the tolerance. Does not take into account whether it's centered or not. A lot of people call that the process potential. So if it was centered, this was the best it would be. On the other side, once you add that little sub K for CPK or PPK, you're getting to the actual process capability. And again, it's where you actually look at where the mean is in reference to the spec limits. So therefore, you get an actual process capability. Now, here's where there are some differences depending on what part of the world you're in. In North America, CP tends to mean short term, and it's using the potential performance, while PP is the long term or the actual performance because it's taking into account a lot of variation over time. Again, in Europe, it's typically reversed. It doesn't matter. Just be sure that when you're reporting to your customer, you know which one they want to see and what their definition is. All right, now, here's a general roadmap. We already kind of talked about this, but if I'm gathering data, first thing I'm going to ask is it attribute or variable? If it's attribute, I can calculate that PPM number. If it's variable, I start looking at the means and standard deviations, and I can calculate the CP PPKs. But again, I can convert that into a sigma score, which can be both converted into a PPMs or DPMO and a Z-table. So again, just a little roadmap of what we just mentioned, but they all come together when it comes to either PPMs, DPMOs, and the sigma score. Here is a top tip. If you ever calculate a sigma score and someone asks you to calculate a CPK, there is a general or rough estimate by multiplying the CPK times 3 to get the sigma score. For example, if you had a 1.33 CPK process, you would multiply it times 3 and you would have a 4 sigma process. That's just a quick top tip. All right, so we've talked about variable attribute data, so we know the data type, we've characterized that. Now we have to understand, is it representative? The fact is, every time we take a sample, it's not going to be the population, and we know that, you know, we took every single one, that still doesn't guarantee the next sample is going to be the exact same as the previous, you know, 1, 10, 1,000 samples, okay? So we always know we're taking a sample, The question will always become, when we want to characterize a capability, is the sample that we took representative of the population? It's not going to be the exact population because we know it's constantly changing, but is it representative, right? Now, when we have, and very typical in the aerospace industry, very small batch sizes, that's where we run into this problem. We really have to understand all of those sources of variation that Jennifer talked about. Do we know those common cause variations that are going to exist every day between shifts? And over time, do we start getting the special cause variation? If we truly want to understand the process capability, the first question we need to ask ourselves is, how many samples and what number of samples make it representative of the actual process? Now, there's a little asterisk here because a lot of our customers will actually have specifications or qualifications to a representative sample size, so you may want to consult your customer. All right, now, along with that, and this comes into play, is do we have subgroups for our samples? And what does that mean? Typically, we take a sample size of 3 to 5 for a subgroup. That's if there is a natural subgroup. It doesn't mean there has to be. Typically, in small batches or in small size, lot sizes of 1, you don't necessarily have to have a subgroup, but you should always ask yourself, if I want to be representative, do I take a subgroup? Is the data biased? For example, representative would mean that I accounted for all sources of variation, or as much as possible that would make it representative of the population. If I have 5 operators that run the machine and I only use 1 operator, could I really claim that 1 operator is representative of the process? It could be, but you should always ask yourself that to make sure that that's not going to be biased to the 1 operator. And then lastly, you should always ask yourself, does the data make sense? Are there responses that surprise you? In other words, when I look at the data and I see spikes in the data, or we'll talk later about a control chart, is there a reason why it looks like it's out of control? So always look at the data as a whole, run a distribution on it, and we'll talk about that in a minute. All right, now, as we mentioned, there is variation over time. You can see in this example that we took a data set and kind of have a moderate amount of spread in sample set 1. And then in sample set 2, it looks like the spread of the data got a little bit wider with a little bit more out of specification parts. And then in data set 3, all of a sudden it was very, very narrow. Now, when you run a control chart, hopefully this variation will show up because it seems like it is more than common cause. You may be seeing some special cause variation. But the intent of this is to show that you could have shift over time. As we say in quality, shift happens. So you have to make sure that you understand, are we seeing that shift over time, and how is that represented in our data set? And here's just, over time, over many, many shifts, over many, many, days. Maybe this could even be within a day. Maybe in the morning the machine runs a little cold, and so you kind of get on the low end, and then as the machine warms up, it goes to the high end, and maybe it drifts back down. I mean, these could be, over days, over shifts, over operators. But again, looking at this short and long-term data, right? Sample set 1 is short-term because it's within an operator time, a shift, or whatever. Are we seeing this? And it's very important, again, to understand our representative sample if we're going to see this over time, because the last graph at the bottom, this is total sample set, represents if I just stacked all of the data from above down at the bottom, and you can see the variation will look a lot different over time than any individual sample set. All right, so that's why it's very important to understand that variation that we're seeing. All right, just a little bit more information on that. Again, in each individual day, you have a small amount of variation. That's called the within each sample set or each day if it was a day. And you can see as you look between days, that's your between group variation. And then obviously when you stack it all together, you're seeing the variation of the between and the within in one big data set. Now, as we talked about another process characterization, it says make sure you understand subgroups and subgroup size. It's very acceptable and actually wanted that you would use each one of these sample sets as a subgroup. If within each sample set you have common cause variation only, then that would be a great way to make a rational subgroup. And it could be over time, as I mentioned, maybe the machine's warming up, over location. For example, that could be different machines. So sample set 1 is machine 1, 2, 3, and 4. Could be operators that are running these parts. It also could be part type if you have some way of commonizing the data and graphing it because it's all a whole with the same tolerance, but maybe the material runs slightly different. So again, these are ways of looking at it as a rational subgroup. And you'd want to plot it as a rational subgroup because we'll talk about what that does to your control charts later. All right. Now, in general, when we start graphing these, you can see that if you had a narrow distribution, most of the samples are within, or almost all of them are within the tolerances. And as you get wider with your sample distribution, you're going to have more defects. So takeaway is here that as standard deviation increases, obviously defect levels will increase. And really, standard deviation is called the sigma. And so therefore, as the actual standard deviation goes up, the sigma level actually goes down. And the sigma level technically is just a measure of how many standard deviations away from the limit that you are based off of the width of that standard deviation. So we always want to reduce the standard deviation to increase the sigma level. All right, and that's talking about just a pure defect probability versus standard deviation. And here's another example where if you just weren't centered, what would happen? In other words, if you had a process that was centered versus not centered with the same exact standard deviation, you can see just by being off center, you're creating a lot more defects that are below the lower spec just because you are off center. So again, the two problems you generally have is either a high standard deviation creating defects and a low capability, or you are off centered and you have a low capability. In either case, there are things to do to fix it, and that is called managing your variation. All right, so that's all the theoretical discussion we're going to talk about today. Now let's get into the actual, an example. So we'll start with that first one, which talked about attribute data. So in this case, we had a process capability study we wanted to do, and our customer told us if 60 Rockwell hardness is or less is acceptable, and a result greater than it is unacceptable, we'll treat it like an attribute. And if you look on there, you can actually count the number of defects that you have. And if you count that up, this is the numbers that you get. You actually have 6 defects out of the number that you have there, out of 30 samples. All right, 6 defects out of 30, that's about a 20% defect rate. Again, going through my little flow chart, and I just assumed an opportunity count of 1. You have a DPMO of about 200,000, or 20% converted to DPMO is 200,000. I go to my sigma scale Z table. I actually would get a 2.3 sigma process out of that, which is, if again using the simple math, I could divide by 3, and that's about a 0.8 CpK. All right. So again, that is a way to measure. And if I was going to say that this data was attribute in terms of my results above or below 60, I could actually report my capability in that way. Now, is there a better way of reporting this? Absolutely. This data looks a little bit more variable than attribute. In other words, that it has a continuous scale, which means that we could actually report a mean and standard deviation, actually calculate the CpK and determine how the process is performing. All right. So the first thing I do, you can do this either in the statistical software package or even Excel, but you can actually calculate a couple of key elements to process capability. The first one is going to be the mean. and in this case it's 45.3, the standard deviation, which is 16.3. And then given the one-sided spec of 60, we can use that information to calculate our process capability. Now, what you'll notice in here, I've also highlighted the fact in my statistical software package, the Anderson-Darling p-value. If you understand this, or if you don't, I'll explain it. This basically is telling me that a value above 0.05, I can assume normality, or at least at a lower risk level, I'll assume normality. Whether the data is normal or not is neither here nor there, but it just approximates the fact that I'm okay with my assumption that it's normal, and I can use capability indices which use normality, such as CpK, as well as control charts. So, looking at this, I have normal data. I know the mean and standard deviation. Now, let's compare it to the actual specification. All right, again, I can use a software package. I can actually calculate it. By the way, all of the calculations and the general formulas are listed in the back of this presentation, so you can, at your leisure, you can look those up and calculate this manually if you wanted to. But back in the day, before software packages, you did. But it's nice to have a statistical package that does it for you. So I plug this into my software package. I put the upper end spec limit. Now, one of the things that you'll realize, if you look closely, 0 has an LB next to it, not a lower spec limit. In the case of rock wool hardness, it's not a spec limit of 0. It's actually a minimum. You can't be lower than that anyway. So I put a lower bound there. That just changes the calculation slightly for this statistical package, but you always want to make sure if you have a lower bound, whether it's a spec or not, if a lower bound, you can't get less than that number. Put that into your software package. In this case, I did that. And when I did that, it calculated the mean, standard deviation, all that good stuff. It told me that I could expect to have roughly 182,967.35 defects out of a million. And that's my DPMO. That is an actual calculated DPMO using the mean and standard deviation. Now, what you'll notice is the observed. Well, the observed is actually counting the number I had, which is very similar to my attribute. So in this software package, I can either use the observed, which is the number of defects that I saw, or the calculated as well. Now, let's get over to those indices that we talked about before. Again, in the long term, accounting for process variation, we actually had a CpK and a PPK of around 0.28, 0.3. Not too different to make a huge difference. If I multiply that times 3, as I mentioned, I have about a 0.9 sigma level for this process. All right, so again, you can just calculate all of these indices and report whichever one you would like to as far as process capability. And again, as I mentioned, it's not binary. Is this process capable? I'm not sure I can answer it as yes or no, but I would tell you that this process makes about an 18% defect, 18 to 20% depending on how I'm measuring it, or it's at about an 80% to 82% good level of quality. All right. As I mentioned though before, it's not just important to calculate the process capability, you also have to understand the control, right? So we can determine that, but if we do not have stable processes, we really shouldn't be reporting capabilities. So we always have to make sure that we have a stable process. We typically do that by an SPC chart. Also, the statistics aren't valid if you don't have stable processes, as well as you don't know if they're consistent over time, right? And again, as I mentioned, control charts help verify all that. All right, now, here is a very good way to understand how control charts work. If you did not know this, a control chart actually looks to see and this is some common sense way of looking at it, what we expect to be common cause variation. Now, that is a broad term versus special cause variation is a broad term, but how could I quantify that in a way that I could truly understand and make use of that information? It's kind of like process capability. It's a broad term, but we don't, we say process capability is something to within something. Well, for stability, what we're saying is that the data is represented by 99.73% of the data is within something. And if it's not within something, then we call it special cause. So the one that you are typically seeing on a control chart would be the plus minus 3 standard deviations of the mean. Well, plus minus 3 standard deviations makes up 99.7% of the data. All right, so if I do the math and look at that, that means 3 times out of 1,000, roughly, outside of those control limits. And that's why we call it control limits. Well, if I split that in half, what it really means is only about 1.5 times out of 1,000 am I above the spec limit, or 1.5 times I'm below the spec limit. So really, a rough estimate of what we're talking about with common cause and special cause is that 1 out of 1,000 times that thing is expected to happen. If it's not expected to happen 1 out of 1,000 times, then we call that special cause. All right. Now, if I apply that even further, and people do, so besides the plus and minus 3 standard deviations, which we are accustomed to seeing on control charts, we also have trend lines and other things that can be used as limits for special cause variation, okay, which will flag and say that, no, this is special cause. Believe it or not, if you do the math on those trends within the numbers, 4 out of 5 times, or, 1 out of 3 times above this in a row, those are actually mathematically, again, 1 out of 1,000 times happening. So if you did not know this, this is the way that we've determined whatever special cause. It was only supposed to happen 1 out of 1,000 times, and it happened more than that. So if a number is outside of those, we wouldn't have expected to happen, so therefore that is special cause. If it's not happening and you're not seeing any of those trends or those out of control limits, then we actually say it's statistically in control. In other words, that it's predictable. All right, so here's just an example overview of what you see on a control chart. Typically, you'll have plus minus 3 standard deviation as your control limits. Anything above and below that is just a violation of control limits. You have the numbers in order. They are in time order. I've seen that as a common failure mode where sometimes people like to order them not in time order, but in from high to low or low to high for whatever reason. So you get this weird trend line down. Obviously, that will actually flag immediately as a control limit violation or a control violation of a special cause. You have a control limit, and your mean is typically plotted as well on your control chart. Now, what I would mention is that typically charts look like this, and if you're dealing with normal data and you want to do a chart of just normal data, you have a center line like a mean, you get upper and lower control limits. But if you had other distributions besides the normal distribution, you can actually create charts for non-normal distributions as well. But the control limits are the exact same, about 1 in 1,000 that are going to be out of control. They may not look as clean as being equal on both sides as a standard normal chart would. And again, as we mentioned, if you actually look at the chart and think about it, it is plotting plus minus 3 standard deviations. So if you actually took that data off, it would look like that distribution on the right-hand side, and that 99.73% of the data should lie between the plus and minus 3 standard deviations. Again, the expected region of control versus out of control special cause variation that is in the blue region. All right. Again, we expect to see common cause, right? We may not want to see common cause, in other words, a lot of variation in our process, but that's the voices of our process. That's what we see. If we see special cause, We're seeing the voice of our process having assignable or not inherent to process. You know, maybe they're a fleeting event and a one-time event that happened, you know, a new material you came in from the supplier that wasn't exactly what you wanted, or a new process was implemented, or, you know, a machine broke or starting to go or drift over time, okay, and these would cause out-of-control points. Obviously, the whole point of understanding stability is to know when we have common cause, that's good, and then special cause means that we're running out of control and we won't be able to understand our process capability. Again, as we mentioned, so I won't cover this too much. This is the region of common cause. When it's in the green region, the +-3 standard deviations, 99.73% of our time. And the red region is unexpected variation that we should not have seen. All right. Now, when we actually think about these rational subgroups, we talked about them before. You know, a subgroup is good because what that's going to give you is that within variation, that common cause variation within. Typically, it's the same at the same time with the same setup, with the same people, method, and material, right? So that way we can capture that, right? And we know that that's special cause. And that's why we use subgroups, is because we can capture that as a moment in time with the information that we want. Now, if we look at process variation from numerous sources, right, we're going to take that within group, look at it over time, and we're really going to try to use those rational subgroups to help us determine our within variation versus our between variation. All right. Now, I mentioned this before, but if you have variable data, it's typically 3 to 5 samples, 5 if possible. If you have a high volume process, that should be possible. And attributes, typically you look for a 30-piece sample size to be able to plot attribute on a chart. Now, there's always going to be a balance there. Obviously, if you're taking way too many samples or 100% sample size, then obviously it may be too costly. If you take too few, though, you're going to have unreliable information, not truly understand the variation. Obviously, the more frequent, the more better, but you do have to balance the two. And again, consult your customer, because they may have a certain specification or standard they want you to follow for that. One more thing I would mention is that if you have online measuring systems, there are a lot of them out there. They can measure both the capability as well as stability over time to make sure that you understand the variation. What I will also mention is that to have a good control chart, you should have 20 to 25 subgroups plotted. What I'll also mention is that once you have the control chart limits after the 20 to 25 subgroups, they don't constantly change over time. You should use them unless there is an event or something that would cause you to redetermine or recalculate the control limits with 20 to 25 subgroups. We use 20 to 25. Why is that the magic number? Well, if you actually plot the confidence over sample size, 20 to 25 is a good number to have a higher level of confidence in our decision and our risk assessment. All right. Now, it would be great if we could always use rational subgroups, those 3 to 5, but you know, you have very small lots and very small processes, and you're only making one a day, a week, or a month. You know, that lends itself to not have a natural subgroup. Office metrics many times are only calculated once a day. Destructive testing, that's only once a day. And as I mentioned, very low output volumes. It's okay. You don't need them. It's always better to help calculate the within variation. But there are statistical software packages that will determine the estimate of the short term and the common cause variation. And typically, a program such as Minitab, I'll just add as an example, uses a subgroup size of 2. So in other words, it looks at the individual results. The successive ones assumes the successive results are within group variation, as opposed to the 5 results in a row are the within variation number. So it actually will calculate that as a rolling number, and I would say use that default of 2 as a good reference for determining the within variation for process capability and stability analysis when you have individuals. All right, so here is an example of a control chart and a natural subgroup and the effect that it can have by choosing the right subgroup. For example, in this case, it looks like we have 3 parts that are measured every hour, and those are plotted by the red dot. So each of the red dots at the top chart represents samples 1, 2, and 3. And the next red dot would be hour 2, samples 1, 2, and 3, and then so on and so forth. And basically, you can see what we're looking at as the within variation is using the samples, 1, 2, and 3 and the standard deviation. That's what's plotted as the control limits. And the between variation is the differences you're getting hour by hour. At the bottom chart, it's basically looking at the variation that you're seeing within each hour's set of data. So that's an X bar in our chart example. And you can see that by the 4th sample that we took, that our parts are starting to exceed the control limits. There's no reference to the spec limits. This is literally just looking at the stability over time. Now, if I take those same samples, but instead of looking at them as hour 1 as a subgroup and then hour 2 as a subgroup, if I took hour 1 and 2 together, I took all of those samples, so I either took 3 samples, or if I took 3 per hour, it could be 6 samples, and plotted that, what this is showing is that I have a lot more variation. Remember, hour 1, hour 2 are slightly different, but if I plot it as 1 point, I'm going to start looking at that within variation, and it's going to be very, very wide. And so when I plot that on a chart, this chart shows that the control limits are actually a lot wider. I have the same samples. I could actually do this with the same samples, but the fact is that my control limits are much wider because I used much more variation for my within. So these subgroup size, you can see, really matters because just by taking more samples, I'm actually able to, I hate to say this, not able to in a good way, but I'm actually masking the variation, the between variation, by taking bigger samples and a wider set of samples with more variation. And in this case, you'll see that if these were, and by the way, mathematically, behind the scenes, these are the same samples and the same numbers, but the variation is combined within, so therefore it looks like I'm in control, versus the previous one where I was out of control. Again, rational subgroups are making sure that it's common cause variation and not that between variation. You have to make sure that that could be a pitfall to under control your process by putting too much variation within your subgroup size. All right. Now, as we mentioned, standard control limits are plus minus 3 standard deviations. We fix it. We take that 20 to 25 samples and we fix the baseline, and we use that. And we never really change it unless we've done something specific to the process to say, okay, let's start over again. And by the way, never ever derive control limits from spec limits. That's not how it works. Control limits are supposed to be the voice of the process, while the spec limits are the voice of the customer. All right. So going back to our control charting methodology, always make sure we understand the characteristic that we're going to monitor and control. We have to understand the data collection point that we're going to be taking it from. We look at the control chart. Again, do we have subgroups or not? That'll help understand what control chart we're going to use. We start with the type of data that we have to make sure that it's an attribute versus a variable. If we do have rational subgroups, make sure that they are correct rational subgroups. From that, we collect and choose our sample size and frequency. Again, 3 samples per operator, 3 samples per hour, whatever it's going to be. Make sure that the measurement method is good. Now, we talked last month about measurement system capability. So make sure that the system is capable of measuring the variation. So we talked about that last month. Your system has to be able to measure the capability and capable of measuring that variation, because if not, your control chart will look pretty flat. Make sure that you have the initial data, the 20 to 25, to create the control limits. You set it up, you chart it. Make sure that there's a procedure, and then maybe it's a system that's charting it on a consistent basis. Make sure you train your personnel, and then you can actually institutionalize that, and people are using your control charts. All right, so let's go back to our example. And the example here is Rockwell hardness. I already calculated the capability, but what I didn't do is make sure that it was stable. All right, so I look at my data. What type of data do I have? I have variable data, okay. What type of chart would you use? Well, in this case, if I knew, I have to know a little bit about the data, so I'll just assume that, you know, we take one data per day over the past 30 days, you know, one a day, so that's just an individual. I don't think there's a natural subgroup that I know of here. And then the last question, so I'll maybe use an IMR chart. Does specification play a role in the chart selection? The answer is no. As we mentioned before, specification has nothing to do with any limits, has nothing to do with the chart. We will just use an IMR chart using our control limits, not our spec limits. And I did that in this example. I put it into my trusty statistical software package. I ran it. I put in, you know, the standard control limits plus minus 3 standard deviations. I don't see any special cause there. I look below at the moving range. There's no special causes there. As I mentioned, there's a lower control limit. Always going to be of 0, by the way, of a moving range, because that means the samples did not vary over time. But anyways, everything looks good. So I can trust my capability analysis that I ran early because my stability analysis shows that I am in control. All right. So here's just a general, with the most commonly used control chart selection process. Again, starts with, do I have variable or attribute data? Okay. If it's variable data, is there a subgroup size? Yes. And then if it's individual, no. If it's greater than 9, if it's not, use an X bar and R. If it is, you can use an X bar and S. If it's attribute data, use proportions. You either have counts or you have defect size, defect proportions. So you can either use a count or a P chart. But those are just the standard ones to use. Typically, I use an X bar S, an IMR chart. By the way, you can also use target IMR charts when you have features that are very similar for very similar processes, and overlay them on a deviation from a nominal chart. Just some top tips for charting. Again, for attribute data, as I mentioned in the selection process, typically if you have defects, you use C charts and U charts. And if you have defectives, which is a proportion of the defective parts that you have, it's going to be a P chart if you can do it as a percentage. If not, if you have a constant sample size, you can use an NP chart. Okay. In general, obviously, to running control charts to identify special cause, take action without over-controlling or tampering with the process. But as we mentioned, a big tip is to make sure that you have a rational or a good rational subgroup so you don't over or under control your process. All right. As I mentioned, never sort your data. It always should be in time order is the only sorting you should be using. In other words, do not sort it from high to low. Do not sort it by operator. It should be just straight time data. Incorrect decisions can be made. Again, as we mentioned, it's about 3 times out of 1,000, but if you split it to the either side of the control limit, it's about 1.5 to 1 times out of 1,000, so keep that in mind. That's the general rule of thumb. If it's occurring 1 in 1,000 times, then it is out of control. Range charts, out of control results in loss of signal. In other words, when we have way too much variation within, we're going to lose the signal of whether it's a special cause or not. Control limits are not the same as spec limits. Please remember that. One is voice of the process, one is voice of the customer. And special cause variation may occur within control limits. These are seen as runs, trends, and patterns. In other words, not only do we look at the plus minus 3 standard deviations, we always look at trends and runs to make sure if we have special cause happening. So I think this is my last chart, but basically how some people have asked me, how does process capability link to tools such as FMEA? Well, there is a column in FMEA that talks about occurrence. if I look at this occurrence of this feature, hardness going out of tolerance, it happens 20% of the time. I actually can use that as a failure mode as the occurrence of that failure, which is out of spec hardness. So I can use that number and put that in the occurrence column in FMEA using my table of 1 to 9. All right, so there is a very direct linkage to FMEA and process capability. All right, now I'm going to transfer control of the presentation today to Mark. Give me 1 second, Mark.
Can you guys see my pointer moving around, Peter?
Not yet. Now you should be able to take control.
Okay, yeah, something just said take control. Okay,
All right.
talk about key characteristics. The first slide I want to talk about here is, did I do that or did you do that, Peter? Assume that I did that. I want to talk about location of key characteristics. We've been talking about process capability and control. If you notice in this chart, you see key product characteristics are toward the center of the picture here. We felt it was best to group it in this discussion because this is where key product characteristics and variation control really come together. But they are at different points. They are at different points of our APQP process. Okay, key characteristics chain. This is kind of a good document because it shows kind of a logic path, a very high level logic path of where key characteristics are created from. So you get customer expectations through many different documents. They can come through design specifications or any type of functional performance specifications that you can get from the customer. From there, with the customer, you develop special requirements, the things that we feel are going to be documented in some form of print or specification for us to follow. From there, you establish critical items. This is the first time where we see the CI indicator come in. And you can see from the definition, these are items that have significant effect on product realization and use of the product. They include everything: safety, performance, fit, form, function, all aspects that could need some type of additional attention in our design process and in our manufacturing process. The movement between critical items and product key characteristics, this is probably the most difficult to make, and where most of the controversy comes about when we talk about key characteristics. Most of the debate comes about the key characteristics are a subcategory of critical items. They are a category that deals specifically with variation sensitive characteristics. And we're going to talk about that a little bit later in the presentation. The big debate that comes from key characteristics, and the reason that sometimes this is akin to talking like about politics with other quality professionals, is lack of other types of critical items, definitions of other type of critical items like safety or regulatory, sometimes force us into thinking that key product characteristics or product key characteristics need to encompass more than they're actually designed to do. And in this presentation, we're gonna talk specifically about that so we can get an understanding specifically what we're talking about when we're just talking about this one form of critical item. The product key characteristics then go down to process key characteristics. Obviously, when you're variation controlling a certain specification, you have to variation control the process characteristics that make up that specification. I like this diagram simply because it shows kind of a logic path. It goes one step further into the logic than the previous slide did. It walks us through a similar discussion though. You gather the voice of the customer. You see we're going from the upper left-hand corner down to the lower left-hand corner, all the way down to what we talked about, the process control plan, through the PFMEA, through the DFMEA, then through the PFMEA. So you gather the voice of the customer. You go through the product level discussion. You decide whether or not there is a critical item. If there is a critical item, then you go down to the orangish block where you see, you discuss what characteristic level it is. This is where you also make a variation management discussion, whether or not this characteristic is key to variation control. Then this feeds back into the DFMEA, PFMEA, then on into the production control processes through the flow diagram in the process control plan. So let's talk about key characteristics specifically. This chart is specifically designed to try and focus us on what a key characteristic actually is and what it actually isn't. This chart here specifically speaks to the customer, I want to say excitement, but the customer enthusiasm around a variation reduced product, variation reduced characteristic. This one specifically defines the key characteristic as being, as you reduce variation in this characteristic, it creates an increase in enthusiasm. It creates a happier customer. And this is absolutely essential to the key characteristic definition. A key characteristic shares an importance across the specification, not only at the specification limits. So once you cross the specification limits, you become within print. That's where a key characteristic kicks in and says, okay, at the specification limits, you are meeting my minimum requirement. But there is a great advantage if you can get me to the center of the requirement. And this is why we mark these as key characteristics, because this is where we want to do variation management. This is where we want to spend our money on variation control. And the graph on the little chart on the bottom right hand side is the one that's trying to illustrate this. As you move down in the standard deviations or up in the CPKs, you are increasing the excitement at your customer. The end user of the product can feel the variation reduction. And that is absolutely essential for defining a key characteristic. If it is something that is linear across the specification, in other words, I reach a threshold of acceptance at the spec limit, and that threshold of acceptance stays the same all the way to the next spec limit, then that's not a key characteristic. That can be a safety characteristic, it can be a reliability characteristic, it can be many other type of characteristics, but key characteristics must have some sensitivity variation specification. Okay. Try this again. Okay, up to this point, I've been able to forward the slides, but Peter, I think I'm having problems doing it now. Thank you. Back one if you could. The previous slide, Peter, if you could. Yeah, thank you. Okay, what are key characteristics? This is it's a very simple diagram trying to describe this in a real world application, if you will. The intention of the customer key characteristic, the one you see encircled, is you would assume that to be like some type of panel gap or door gap or something. Use it in aircraft or in automotive. To say the gaps between the hood and the other panels, quarter panels, or the gaps in the doors. And what you want here why this would be a key characteristic is this has become an attribute over time of being some indication of quality or variation control in the product. So when you look at a car or a plane and you see inconsistent gaps between the doors and the windows, where one gap is large and the other gap is small, or a gap converges, starts out large and becomes small, this tends to become an assumption of poor workmanship or poor quality. So this has become a key characteristic, that these gaps maintain consistency. I just got to note that audio is going in and out. Let me try and get closer to the computer. This consistency gives us the assumption that we have quality or performance in our product. So keeping these gaps consistent, reducing variation between gaps gives us a feeling that we have a quality product. So this has become a key characteristic because this becomes a variation sensitive attribute. And this specific diagram tries to show not only the key characteristic, which is the end gap between the little arrow on the top and the block on the bottom, but also what we would call key process characteristics that go to make this up. So the end gap is the result of the addition of many other process characteristics or even design characteristics that are separate from the final key characteristic, the customer characteristic, that end up going and making this final variation in gap. So all of them must be variation controlled. They become key process characteristics if they are process control attributes. They remain as internal key characteristics if they are internal design aspects that lead to a final customer key characteristic, all with the intention of reducing the variation in this gap. So this is a very good definition, because specifically what we're talking about here, there isn't really a threshold, and I'm going to use the increasing gap, not closing gap. Obviously, there's a threshold if we make contact. But if you look at from the increasing gap side, it's difficult to say at what point the gap would become out of specification. What happens here is really from the fact that as we introduce more variation, we simply become less satisfied. It's tough to say when you reach half an inch or quarter of an inch or whatever, this is the threshold that becomes out of print. Now, we certainly would have a print characteristic for this, but really this characteristic shows as we increase the gap, I'm becoming less satisfied. Or when you're considering gap to gap comparisons, when the gap difference between the gaps increases, I'm becoming less satisfied. And this is the key for key characteristics. Okay, yes, got control again. Okay, this is kind of a funny example to try and illustrate this as well, but I've seen this example used many times, and it's a good example. So what you're seeing here is a soccer field that would obviously exceed a spec limit. This probably would be too difficult to play soccer on, but at some point, this soccer field, as it levels and flattens, is going to hit some type of specification limit that is our threshold that we're willing to pay for. But that didn't become any greater or less than just previous or just after we started to flatten it. What you got here was the soccer field got gradually better every time we flattened it. And it would become the best being perfectly flat. This is a great example of a key characteristic, because what you can say is at some point I crossed a threshold that I'm willing to pay for, which is my spec limit. But that was just incrementally better than the previous level, and it's only incrementally worse than the next level. So I didn't really cross a threshold where I said it became good, it became great from bad. I merely crossed a threshold that I'm willing to pay for. But the key characteristic, the reason it's a key characteristic is because what we're saying is as you continue to flatten it, it will continue to get better. It will get better all the way to the point where it's perfectly flat. So this becomes a great example of a key characteristic as opposed to one that meets a threshold, the threshold of acceptability that becomes equally acceptable across the spec limit. Okay. Peter talked about this earlier. The reason this is in here again is because this becomes a very important part of our key characteristic control. Key characteristics themselves can no longer be controlled like attribute dimensions, things that are good or bad, things that cross a threshold. They must be variation controlled to reduce variation. That's the whole intent of this identifying key characteristics, is that so that later in the process control, we understand where it is that reducing variation adds value. That's very important. This controlling it to the spec limits is no longer good enough. Okay, that is good enough to meet what the customer is paying for, but it's not good enough to make the customer enthusiastic. What we need to do then is control the variation and reduce variation toward the center. And this is specifically one of the tools that we use to do that. Statistical process control is a great tool to use to continue to identify a CPK or standard deviation, and identify when we are successfly improving our variation reduction and therefore improving our customer enthusiasm for this characteristic. And this would be used for not only the final customer key characteristic, but also many of all of the process key characteristics as well. Okay, this is a page where we show some of the references for all of the stuff that we've talked about today. We got quite a few reference documents here, some of which we pulled information from for this presentation. These are great places to go to continue to learn about these tools and these processes. The relationship, again, that we talked about here, the process capability and control, this is what we discussed today. This will now move in later into the PPAP approval, which I believe is the next webinar. The next webinar is on January 21st, and this would close out that webinar series. I believe it's on the next slide as well. Yep. Then this shows us the January 21st webinar, the PPAP, which is the final step in our APQP process and the recurring step that occurs into our legacy production. Okay, I'm going to go quickly through some of the reference materials, mostly what Peter talked about. In fact, I think they're all what Peter talked about here. You see the short-term indices, which is our CPK controls, CP and CpK controls, long-term, which is our PP and PPK controls. Peter talked about this. These are some of the tools that you can use. This is how he represented graphically some of the relationships between CP and CpK, the centering portion of it. Some of the guidelines around trying to show what is good and bad CPKs, especially for key characteristics, that is actually defined for key characteristics in APQP, what is required for CPKs, and the relationship to our Z tables or our Z numbers, which shows a relationship between the CPK and actual defects that we see from the products. I think we're at the question and answer. I think, Sue, this is where you're going to take over. And I don't know how to give you control. I think Peter has to do that.
Sure is. You can just move it to the next slide.
Okay.
Thank you. This is one of the questions people are asking the most. But first, let me thank you, Jennifer, Peter, and Mark, for being panelists and going through the slides to this point. We're going to have we do have a few questions for you from the attendees, so we have about 15-20 minutes to answer some of those. But first, I just wanted to introduce myself. If I haven't already spoken with you on a previous webinar, my name is Susan Parsons, and I work for the IAQG, supporting the product and supply chain improvement team and the SCMH, of course. To answer some of the first couple questions that have come in throughout regarding these slides, the deck, and the recording and possibly Q&A. If you go to the website of the SCMH, you'll notice that the IAQG is updating their website. there is a link still to the SCMH, which we will be updating this year. I believe the first half. This will look pretty new to everybody. We're going to try to make it simpler for everybody to move around in it. I've included some slides at the end of this presentation for your review if you haven't already become a registered SCMH user, which is free, and you'll be notified of future webinars. But if you look across the top, you'll see 1 through 7, the various sections of the SCMH. There's one called webinars. In that webinar section, all previous webinars that are still relevant and up to date are posted there. Usually you will see the presentation itself, possibly a Q&A if we've put one together for it, and then the recordings. The recordings become available within about a week of an actual webinar, and it's all based on whether or not the audio quality is good and it's coming across for us to use it. In that case, we'll post it. So there, for the previous series, there's already recordings available, and this one will be posted in about a week, pending review. So with that said, that tells you where you'll find this information in the future. And I have a couple of questions. The first one, I believe this one is pointed toward you, Peter. Capability is defined % good versus bad, % good/bad versus spec limits. However, can it be against internal control limits too?
Yeah, I mean, the only thing I would guard against is that control limits technically are supposed to be standard deviations based, not because you call them control limits. But instead, what I would say is internal spec limits, as opposed to control limits, are commonly used. And you could calculate your capability based off of the internal spec limits, what I would call internal voice of the customer, to calculate capability. But if you're going to report number to your customer, it should be against the spec limits given by the customer. But yeah, you could have two capability indices, one for your internal spec limits versus your external spec limits would be the other capability indices, which is fine. It's basically just what you're going to use in your formula, whether you're going to use your customer limits or your internal limits. Obviously, if your internal limits are tighter, that means your capability will look not as good because your process, which will remain constant, is going to be gauged against a smaller tolerance. So it won't look as good. but I would recommend your customer reporting it to his or their spec limits.
Thank you. How could this be applied to software coding or software performance?
Typically in software coding and performance, what I've seen is using defects or number of errors seen. So if you wanted to report your capability for software coding, you could either do it by number of defects per code. In other words, that denominator would be typically attribute, the number of defects in a line of code divided by the number of lines of code. And your subgroup could be either each individual module of code, or it could be each coding product, or it could be each coder. It just depends on how you can collect the data. But it can be applied, but typically it's on the attribute side, not on the variable side, because the code is either correct or incorrect. And so you could plot it that way. You could measure your capability that way, and I would do control charts on the attribute side. And you could either do it as a NP chart or even as a C chart. The number of defects that you're finding or the number of defectives would be the whole module or set of code. But yeah, I've seen it applied, but you are going to be on the attribute side.
Okay. If you need to go to slide 31 for this question, the distribution goes into negative number. Is that acceptable?
What I believe that slide is talking about is that it does not. There was a lower bound listed there. The distribution is actually, though physically represented by a line, it is not. By putting 0 as a lower bound, the actual formula that's used is not going to count anything below the lower bound, but the way the software package depicts it graphically, it does not stop at that 0, even though mathematically it does stop at 0. So the answer is complicated, but I would say the answer is no, it's not good to go below 0. But it's okay in this case because I know that the software package is not actually using anything below 0. It's just graphically representing it as a normal distribution, even though you're going to have a lower bound. Technically, it's not. But mathematically, it is not accounting for that, or it's accounting for the fact that it does not go below 0. So it is fine. And it's good. Well, very acceptable as long as you make sure that you put that stipulation that it's a lower bound.
And this one's for 33 and 34, before you go back to slide 70, 33, 34. What if the process can't be centered between USL and LSL? Example, we measure a contaminant with limits 0 to 30 mg/L. How should our process be targeted in this situation?
So it's very similar to the Rockwell hardness. I'll use that as an example. I mean, you're probably not going to be able to center this process, or maybe you can, but you also have a lower bound. So the fact is that you try to make sure that you can do one of two things. You try to make sure that you are going to have a capable process, and if the limit is, if you want a CpK of 1.33, one of two things. You either have to move it over the center so it's far away from the upper spec limit, I'm just using this example, or you have to reduce the variation that you're seeing. Either way, if you can't center it, lower bounds is a great example of that. Typically, you don't want, stuff at the lower bound. So what you're going to end up doing, because it's not physically possible to have a 0 hardness, you're going to try to make sure that you're away from your upper spec limit or whatever spec limit, at least typically 3 standard deviations or 4 standard deviations, depending on what you want to achieve, a CpK of 1.0, 1.33. If you need a 6 sigma process, CpK of 2, that means that you either reduce the variation so you have 6 standard deviations away from your upper spec limit, or you move the center away so it's 6 standard deviations away. Again, if you want a 6 sigma process. So if you can't center it, it's fine. You got to reduce the variation, but you also have to understand what your risk, what your acceptable risk, what your CpK you're shooting for. Again, processes like that is very common. You can't center it, but you should always be shooting for having that correct level of CpK that you're shooting for. 133, 166, 2.0, 1.0. So that way you are away from the spec limit. And it's okay not to be centered.
Okay. Very low output volume. Aerospace sometimes fits into this category, and lot for lot is normal, i.e. batch level of 10 to 15 pieces. How do you address this low volume?
So one of two ways. It depends. I mean, I don't know what your sampling level is in your low volume batches, because that's a lot of times is customer based. But if you have a certain, level of sampling, I would use that as your rational subgroup, and then you plot that. If it doesn't make sense, if you're only sampling 1 per lot of 10, then that is your rational subgroup. But you should be plotting them based off of your sample size and what you agreed upon with your customer. And, you're going to have to always get 20 to 25 samples to start your CpK and your stability charts. So just keep that in mind. And when you're calculating those indices to start with, just bear in mind that it's going to take a while before you can report a true stability or CpK. So time is your friend, or you go to 100% sampling so you can get enough data points to start charting that. Again, making sure that you have the variation accounted for. What I've done in the past sometimes when I've had this problem is that I start with my 20 samples, I do 100% sampling, and then I just make sure as I add more lots and sample sizes that it seems to fit within that and no special cause variation is popping out at me. And so I use those starting, points of, 20 samples, 25 samples. And then as long as it seems like I'm not getting special cause variation, then my original assumption is that I've accounted for my special causes. Okay, if I start getting it, then I start looking at, what is it that's causing those special causes and try to adjust my sample sizes and rational subgroups to account for that, if that's going to be part of my normal process, or is it truly a special cause? So I just start with the 20, go from there, and start looking to see how my data fits into that original assumption.
This next one is sort of very similar. You might have covered it, but when doing a PPAP, process capability is key element. How do you handle this when the quantities are very small and it may take a year to get enough data to do process capability?
Yeah, so that's got to be a very specific question with the customer. Again, 100% sampling, and if you're still not at the minimum requirements from your customer, then we'll have to either figure out a way. Some customers may allow similar processes, similar to FAI. If you got, the same product with the same features of the same process, you might be able to use, that type of similarity for your process capability. But again, these are typical questions for your customer. I've seen that, but you always have to ask your customer what's acceptable as far as similarity goes.
Okay, slide 51. Occurrence from this data will be in the P-FEMA. The D-FEMA format developed for aerospace does not have this input for occurrence.
Okay, so there's two different things that we're talking about, P and D FEMAs. So a P FEMA is on process, so that's really process capability focused, so occurrence is related to that. D FEMA, we talk about occurrence, that's the occurrence of a design failure. So I'm not sure, if you had a control chart and a process capability of design failures, very different question. You're not supposed to put the occurrence of that in there. So I think maybe the question is this really for PFME? And the answer is yes. So maybe, I'm not sure, maybe I would modify the slide to talk about PFMEAs more than DFMEAs, but there is an occurrence in DFMEA. It is for design failures occurrence. Typically you don't see process capabilities on design failure occurrences. They would be with some other type of evaluation. But I'm not 100% sure of the question, but this is really mostly for process FMEAs. For design FMEAs, there is still an occurrence. It's just the occurrence likelihood of the design failure versus the occurrence of the process failure.
Thank you. The next one's just a statement, and it must have been within a couple slides after that. We call the VOC voice of the customer. So I don't know if that was just 3 letters, that an acronym that we use slightly different. So
okay,
just for our knowledge. And would another way of saying it? Oh, okay, so this one is for the slide with the. I believe this is for Mark, with the slide with the football field, I think. Would another way of saying it be a non-key characteristic is like kick a field goal. In the goalpost is good enough, but key characteristic is downing the punt within the 1-yard line.
Yes, it actually is. So maybe to use that analogy, if you kick a football and you get it down to the 20-yard line, that's acceptable, where we all think that the punter did a good job. But boy, if he could nail it at the 5-yard line, he did a better job. I think that's an analogy.
Yeah, okay. Let's see, just looking for another one as I scroll through some of the questions. I think this one's for Mark. Please, can you tell a little about the Z table? And it didn't refer to a slide number, sorry.
Yeah, so the Z table's relationship to defects, and actually, Peter, I think you were the one that talked about those, weren't you? Yeah,
I talked about a Z table. So basically, they're typically in the back of statistical books. If you can look up in one of 2 ways. You can either, if you know the defect level, the number of defects you're getting, it'll actually give you the Z score, or the other way around. If you know the Z score, it'll tell you the number of defects you're getting. In effect, if you want to calculate your Z, it is the number of standard deviations away you are from the closest spec limit, and then basically translate that into the number of parts defective. It's also the inverse, or 1 minus the area under a curve of a normal distribution. So it's the number of defective. That's the Z table.
Okay. We only have a couple minutes left, so I wanted to give each panelist a chance if they had anything summarized or something they might have passed over and would like to speak up now about it. So I'd just give everybody a chance to say that. While you're thinking of it, I'll have Peter go first. While you're thinking of that, just wanted to let you know that there were some questions that we didn't get to, and I'll pass them on to the panelists. And if we can update the current Q&A in the webinar section for this series, we will do so. So is there anything you'd like to add to that, Peter?
No, I guess thanks everyone for joining us today. It's I always love talking about my favorite topics, APQP, PPAP, and today process capability. So thanks for joining us.
And Mark, do you have anything?
Nope, nothing for me. Thank you for joining us as well.
All right, and Jennifer?
I'm good, thank you.
All right, I want to thank everybody for joining us today for this series of the APQP. And as Mark has mentioned, there'll be one more in this series, and we'll post them in the SCMH as soon as they become available. Thank you for joining us. Have a nice day or evening. Bye.